Since ancient times, stars have been perceived as eternal and immutable, serving as anchors of stability in a constantly changing world. For millennia, the human eye observed no changes in them, spanning lifetimes, centuries, and even millennia. However, modern astronomy has unveiled a captivating truth: stars are not static objects, but dynamic entities that undergo cycles of birth, life, and death. Like living organisms, stars are born, shine for millions, billions, or even trillions of years, and then die, scattering their elements into cosmic space to give rise to new generations. They serve as gigantic laboratories where essential chemical elements are synthesized, and of course, they provide us with the heat and energy necessary for life. In fact, stars are the foundation of everything we see, hear, and touch. Understanding their evolution is key to comprehending the structure of the universe. In recent decades, scientists have made significant strides in unraveling the mysteries of stars. A series of videos will follow, revealing the stages of stellar evolution, from the moment the universe began and the first chemical elements formed, to the physical processes of star formation, their transformation into diverse types and forms, and finally, their death, which gives rise to new life. This first part of our journey into the stellar world will explore the process of star formation, their generations, and the classification systems astronomers use to study them. Thanks to the groundbreaking work of American astronomer Edwin Hubble and Catholic priest Georges Lemaitre, it was established that galaxies are moving away from each other. Quantitatively, this phenomenon is described by the Hubble-Lemaitre law, which states that the recession velocity of galaxies is proportional to the distance between them. The farther a galaxy, the faster it moves away from us. Thus, the universe is in a state of constant expansion. Paradoxically, the Hubble-Lemaitre law implies that at sufficiently great distances, the recession velocity of galaxies can exceed the speed of light. How is this possible, given that the speed of light is known to be the ultimate speed limit in the universe? The key lies in understanding that galaxies are not actually moving apart from each other in the conventional sense. Early in the 20th century, Albert Einstein developed the special theory of relativity, according to which no material body possessing mass can move at or exceed the speed of light. This limitation, however, does not apply to the spacetime in which these bodies exist. Spacetime can expand or contract at any speed. If time could be reversed, the universe would begin to contract until it became an infinitely small and dense point. Why does the speed of light have a limit? Why doesn't this restriction apply to spacetime? And what was the initial state of the universe? These are just some of the questions that still await answers. The Big Bang process can be divided into several epochs. To avoid delving into the details of the earliest stages, let's fast forward to a moment approximately 1 second after the Big Bang began. At this time, the epoch of nucleosynthesis commences. The term, nucleosynthesis, is derived from the Greek words, nucleos, nucleus, and synthesis, creation. As the universe expanded, the density of energy and matter, as well as the temperature, decreased. The temperature plummeted from incredible values with dozens of zeros to a relatively modest billion Kelvin. Additionally, the intensity of photon radiation decreased, remnants of which can still be observed today as cosmic microwave background radiation. This resulted in a kind of cosmic soup, from which the first elements subsequently formed: hydrogen, helium, lithium, and their isotopes, deuterium and helium-3. Heavier elements could only form approximately 400 million years later within the cores of the first stars, where the necessary conditions of temperature and density arose. 1 second after the Big Bang, the bulk of matter consisted of hydrogen and helium in a ratio of approximately 75% and 25%, respectively. The proportion of other elements was less than 1%. This distribution has remained virtually unchanged ever since. Let's imagine a distant future, approximately 400,000 years later. The universe has cooled to 3000 Kelvin, and the epoch of recombination begins. This is a pivotal moment when electrons slow down sufficiently for atomic nuclei, obeying the laws of attraction between opposite charges, to capture them. The plasma that dominated the universe transforms into neutral gas. It is then that the cosmic microwave background radiation, the echo of the Big Bang, is born. These ancient photons, which have traveled through space for over 13 billion years, are still detected by instruments on Earth. They are unevenly scattered but reach us from all corners of the sky, with an average temperature of 2.7 Kelvin. Imagine if the human eye could see millimeter-wave radio waves. We would observe a faint, almost uniform glow enveloping the entire sky day and night, at any time of year, unchanging for millennia. It is impossible to fully grasp the immense energy of this event, so powerful that its echoes resonate throughout the universe's history, albeit incomparably smaller than the energy of the Big Bang itself. Based on the concept of the universe's infinitely small and dense state before the Big Bang, one might assume that matter should have been distributed almost uniformly. To some extent, this is true. However, if the distribution had been absolutely uniform, the first stars and galaxies, as well as planets, including Earth, would never have formed. Here entropy comes into play, a mysterious quantity that always increases. But it has another important feature. Complex structures cannot arise in a system with minimal entropy, nor in a system where entropy has reached its maximum. They appear only in an intermediate range, where complex molecules and compounds, planets, and even life form. Moreover, the maintenance of life requires a constant influx of low entropy, which stars, particularly our Sun, provide. But that is another story. Thanks to gravitational instability, or Jean's instability, the distribution of matter and energy in space became uneven. The name speaks for itself. Statistical fluctuations in gravity in the infinitely small universe suddenly inflated to incredible scales along with the expansion of the universe itself. This led to a heterogeneous distribution of matter, and where there are inhomogeneities, the first complex structures arise, from atoms to galaxy clusters. This is how the first structures, which we call molecular clouds, were formed. They consist of gas molecules. At that time, these were only lithium and isotopes of hydrogen and helium. Molecular clouds are typically 10,000 to 1 million times more massive than the Sun and range in size from 10 to 300 light-years. Their main characteristic is a high density of matter, ranging from 100 to 1,000 particles per cubic centimeter. This might seem like a minuscule concentration, but compared to the average density of the universe, which is about 1 atom per cubic meter, the cloud's density is millions of times higher. Within molecular clouds, there are even denser regions called molecular cores, with densities ranging from 10,000 to 1 million particles per cubic centimeter, which is 1 trillion times greater than the average density of the universe. Astronomers classify molecular clouds by their appearance into 3 categories: dark, translucent, and diffuse. Dark clouds are so named because they transmit almost no light in the optical range, appearing as dark patches against brighter objects. Translucent clouds are less dense and allow some visible light to pass through. Diffuse clouds are the least dense and most transparent. High-latitude molecular clouds are also distinguished. They are unusually positioned, not lying in the plane of the galactic disk but standing edge-on to it. A molecular cloud is the cradle of stars. For a young star to form, the matter must be cold, around 10 Kelvin. This is because molecules of matter at high temperatures possess high kinetic energy, move quickly, and do not allow gravity to compress them together. In the vacuum of space, there is no heat exchange, so the only way for temperature to decrease is through radiation. But this process is very slow, requiring millions of years for hot gas to become suitable for star formation. So let's move on to the fascinating process of star birth. When gravitational forces take over in a cooling molecular cloud, regions with increased matter concentration begin to form within it. The greater the density and size of such a region, the greater its mass and, consequently, its gravitational pull on the rest of the cloud. Ultimately, this region attracts surrounding matter, growing like a snowball. As a result, out of hundreds, or perhaps thousands, of such concentrated zones, only a few remain, massive enough to establish their gravitational dominance in the cloud. It is from these that stars and planets subsequently emerge. Here, it's worth recalling basic physics knowledge about the laws of conservation of momentum and angular momentum, which play a crucial role in this process. Momentum is the product of an object's mass and its velocity. Every particle in the cloud possesses its own non-zero momentum, but due to their chaotic motion relative to the center, their total momentum is zero. However, the situation is different with angular momentum. It is not zero. Angular momentum, or the rotational momentum of a cloud, is a quantity that characterizes the overall rotational motion of a system. It can be expressed by a simple formula: angular momentum equals the product of the cloud's mass, its radius, and its rotation speed. Since the cloud can be considered a closed system, its angular momentum must be conserved, as stated by the law of conservation of angular momentum. However, the cloud contracts under its own gravity, meaning its radius decreases. With the cloud's mass remaining constant, its rotation speed must increase to conserve angular momentum. This is similar to ice skaters who, while spinning, pull their arms inward and accelerate. Unlike an ice skater, a cloud is not a rigid body, so speaking of its initial rotation isn't entirely accurate. The cloud's angular momentum is created by gas flows within it. These flows are all located at a certain distance from the center of mass and possess their own angular momentum. Due to the chaotic direction of these flows, they partially compensate for each other, and visible cloud rotation may not be present. As the cloud contracts, it spins faster and faster. Centrifugal forces act on any rotating body. At low rotation speeds, a celestial body becomes flattened at the poles and bulges at the equator. As the speed increases, the body compresses more severely. An example is the dwarf planet Hayashi, which has an elliptical shape. At a certain rotation frequency, centrifugal forces at the equator can exceed gravitational pressure, which can cause the object to tear apart. To prevent this, a star must transfer some of its angular momentum to other objects. For example, in a binary star, angular momentum is distributed between the rotation of each star around its axis and their mutual rotation around their common center of mass. Similarly, this occurs in systems of single stars with planets. In the solar system, almost all the angular momentum comes from the rotation of the planets, despite their total mass being only 2% of the Sun's mass. Objects that do not receive sufficient angular momentum during formation cannot achieve a stable orbit and fall onto the nearest massive object. Overall, angular momentum in a system is limited. Therefore, single stars with planets and binary stars are common, while binary stars with exoplanets are rare. This is one reason for a fundamental law of the universe. The more objects in a compact system, the rarer such a system is. Having understood the physics of star and planet formation, let's examine this process in more detail. The gas that makes up molecular clouds is attracted to molecular cores, forming a protostar and a protoplanetary disk. The protostar gradually gains mass due to gravity and heats up due to the friction of gas rotating around the core. Sometimes, friction heats the protoplanetary disk to millions of Kelvin. Under the influence of gravity and friction, matter from the protoplanetary disk spirals and falls onto the protostar, contributing to its further growth. This process continues until the star accumulates enough mass to begin thermonuclear fusion. In thermonuclear fusion, light elements, such as hydrogen atoms, combine to form new elements. This process releases energy and electromagnetic radiation, a portion of which we see as light. In addition to radiation, every star generates a powerful stream of neutrinos, particles that interact weakly with matter. Alongside other physical phenomena, it's worth noting the pressure of light. In everyday life, this phenomenon is practically imperceptible, and detecting it with physical instruments is a complex task. However, on the scale of stars and protoplanetary clouds, the force of light pressure significantly increases. Radiation repels particles from the star, and the force of repulsion increases as particles get closer to the star. This property of radiation prevents matter from falling onto the star and, consequently, from increasing its mass. But this is not the only function of light pressure. The pressure of microscopic photons ensures the hydrostatic equilibrium of massive stars. The pressure of light emitted by the stellar core, as well as compressed plasma striving to expand, supports the star's outer layers, hundreds of thousands of kilometers thick, from collapsing. The intensity of the radiation is so immense that a human could float in this light. though their body would instantly turn into a charred piece of flesh. It is important to note that hydrostatic equilibrium is the dividing line between a mature star and a protostar or stars in their late stages of evolution. The radiation pressure from a newly formed star also stimulates the formation of new stars, as it blows away particles from the molecular cloud that can then be captured by the gravity of other stars. These particles, in turn, exert pressure on other molecules, increasing the density of individual regions within molecular clouds and forming new molecular cores. As a result, stars often form not in isolation, but in large groups known as star clusters. Besides radiation, star formation can be stimulated by other astronomical phenomena, such as a shockwave from a supernova, moving at 1,000 km per hour, which exerts pressure on molecules in the cloud, similar to radiation, but significantly faster and on a larger scale. Collisions of molecular clouds or their passage near galactic arms can also initiate the formation of new protostars. In some cases, there isn't enough matter in the clouds for a protostar to become a full-fledged star. Such celestial bodies, occupying an intermediate position between large planets and small stars, are called brown dwarfs. Brown dwarfs are characterized by a relatively small mass, up to 0.08 solar masses, as well as small sizes and densities. After several hundred million years, their emission rates significantly decrease, making them virtually undetectable to an observer. The first stars, belonging to population 3, initially contained no metallic elements, as it was within their cores that these elements first began to form. 3 types of stellar populations, or stellar generations, are distinguished, with the concentration of metals within a star decreasing as the generation number increases. However, population 3, consisting of the least metallic and oldest stars in the universe, remains hidden from astronomers. The reason for this discrepancy between theory and observation is still unknown. Only low-mass red dwarfs from this generation have survived to the present day. Over 13 billion years, they have managed to form a certain amount of atoms of elements heavier than helium, which, thanks to convection, can appear on the star's surface. As a result, their visible metallicity does not correspond to population 3, and such stars are massed as population 2, the more metallic generation. It's worth noting that in astronomy, the term metals has a broader meaning than in chemistry. In astronomy, any chemical element heavier than helium is considered a metal. In comparison, modern stars contain a significant proportion of metals. Our Sun, belonging to the youngest, population 1 stars, is composed of about 2% metallic elements. The question arises, where did elements heavier than lithium come from if they didn't initially exist in the universe? The answer lies in thermonuclear fusion. Throughout their lives, stars create new elements. It all begins with helium, then, provided the star has sufficient mass, carbon and oxygen are formed. The chain of nuclear fusion continues until iron is formed in the star's core. At this point, the process stops because further synthesis requires energy input. Elements heavier than iron are formed as a result of events with enormous amounts of energy, such as supernova explosions. Stars differ in mass, luminosity, and color. How then are they classified? How can they be presented in a simple and understandable form? Thanks to astronomers Hertzsprung and Henyey Russell, this problem was solved. The Hertzsprung-Russell diagram is an important tool for modern astronomers. If you plot the luminosity of stars against their surface temperature, an astonishing pattern emerges. Stars are not randomly distributed but concentrate in specific regions. This is somewhat analogous to the periodic table of chemical elements, where elements are grouped by their properties. Stars located in the same regions of the diagram also share similar characteristics. However, unlike the periodic table, a star's position on the diagram can change over time, as stars evolve throughout their lives. The Hertzsprung-Russell diagram, HR diagram, displays diverse evolutionary tracks of stars, a kind of road map of their life journey. One such track is the Hayashi track, which describes the evolution of protostars where energy is transported by convection. Hot matter rises to the surface, and cold matter sinks to the core, similar to air circulation in a heated room. While moving along the Hayashi track, the protostar contracts, with its temperature remaining almost constant, leading to a decrease in luminosity. On the HR diagram, the Hayashi track appears as an almost vertical line. When a radiative energy transfer zone forms within a star, where energy is transmitted by photons, the star transitions to the Henyey track. For such a zone to form, the star's mass must be at least 40% of the Sun's mass. Therefore, less massive stars remain fully convective. The Henyey track is characterized by the star's gradual contraction and heating until an equilibrium is established between gravity, which tends to compress the star, and radiation, which tends to expand it. This process continues until stable hydrogen burning begins, after which the star moves onto the main sequence. In main sequence stars, hydrogen burning, more precisely, thermonuclear fusion, occurs in two ways, depending on the star's mass. In stars with a mass less than 1.2 solar masses or with low carbon, nitrogen, and oxygen content, the proton-proton chain occurs, in which hydrogen is converted into helium through several intermediate stages, releasing energy. More massive stars synthesize helium via the carbon-nitrogen-oxygen (CNO) cycle. Unlike the proton-proton chain, the CNO cycle is catalytic. Carbon, nitrogen, and oxygen atoms act as catalysts, and helium separates from the oxygen atom in the final stage, regenerating carbon. The transition to the main sequence is only possible for stars more massive than the Kumar limit, which is approximately 67 to 84 Jupiter masses or 6.5 to 9% of the Sun's mass. This boundary is not precise and depends on the star's chemical composition, as well as the theoretical model used. Objects with less mass become brown dwarfs or planets. The main sequence is another evolutionary track on the HR diagram, where stars spend about 90% of their lives burning hydrogen and converting it into helium. The size of stars remains almost unchanged during this phase. This concludes our overview of the initial stages of stellar evolution. In the future, stars can transform into giants and supergiants, tiny white dwarfs and neutron stars, pulsars, magnetars, or even black holes. This overview has covered only some aspects of star formation, not encompassing the full scope of stellar evolution.